Welcome to the Explainer. Today we're tackling a seriously powerful algorithmic technique that turns complex geometric problems into simple, manageable steps. Let's jump right in. So, let's kick things off with a classic problem that seems pretty tough at first. You've got a screen just packed with hundreds of line segments. Your job? Find every single intersection. How do you even begin to do that efficiently? Now, your first instinct might be to just check every line against every other line. But if you have n lines, that's an O of n squared approach. And in a coding interview, that's almost always way too slow. There's got to be a smarter way, right? Well, there is, and it's called the sweep line algorithm. Okay, so let's break this down. What is a sweep line? To really get the core intuition, we're going to forget about 2D geometry for just a second and simplify things down to a basic 1D timeline. Okay, picture this. You're in charge of scheduling meeting rooms. The big question, what's the maximum number of rooms you'll need at any single moment? Well, you could treat every meeting start time as a +1 event, we need a room, and every end time as a -1 event, a room is now free. Now, just toss all those events onto a timeline and sort them. Then you just sweep across it from left to right, keeping a running total. Add 1, subtract 1. The highest number you hit? Ma'am, that's the minimum number of rooms you need. That imaginary line you're moving across the timeline, processing things in order, that is the core idea of a sweep line. So let's recap. The whole point here is that the sweep line is this conceptual tool that just moves across our problem space. It lets us turn a messy, multidimensional problem into a simple, sorted list of events. We're essentially taking snapshots of the problem, one event at a time, which makes it way easier to handle. Okay, that's the basic idea. But how do we actually apply this to our original problem of finding intersecting lines on a 2D plane? To make this whole thing work, we're going to need two key components. First up, we have what's called an event. An event is really just a specific point on our sweep axis, for us that's the x-axis, where something interesting happens. Something we need to pay attention to. For our line segments, that means one of three things. A line starts, a line ends, or, you guessed it, two lines cross. So how do we keep track of all these events? That's where the event queue comes in. Think of it as our itinerary or our roadmap. It's a data structure, usually a priority queue, that stores all our events, neatly sorted by their x-coordinate. It tells our sweep line exactly where to stop next. Okay, so the sweep line stops at an event. Now what? We need to know what's happening at that exact vertical slice of the plane, and that is the job of the status structure. This is our snapshot. It's a dynamic data structure, often a balanced binary search tree, that keeps track of all the line segments that are currently crossing our sweep line, and it keeps them sorted by their y-coordinate. It's constantly changing as we move along. So let's put it all together. The event queue, sorted by the x-axis, is our journey plan. It tells us where to go. And the status structure, sorted by the y-axis, is like our real-time dashboard. It tells us what we're seeing right now at our current location on the map. So to wrap up this section, remember these two things. You have the event queue, which pre-sorts all the important x-coordinates we have to visit. And you have the status structure, which dynamically tracks the vertical order of lines our sweep line is crossing right now. These two work together to power the whole algorithm. All right, we've got the theory down. Now for the fun part. Let's put these components into action and actually watch how the event queue and the status structure work together to find intersections without checking every single pair. Okay, here we go. Our sweep line starts moving and stop. It hits its first event, the left endpoint of a line segment. What do? Simple. We insert this new segment into our status structure. Then, and this is the most important part, we only check for intersections with its brand new neighbors, the one just above it and the one just below it in the status. That's it. We don't have to check it against every other line on the screen. All right, the sweep line keeps moving and stop. This time, it hits an intersection point that we found. So what happens here? Well, at an intersection, the two lines that are crossing literally swap their vertical order. So that's exactly what we do in our status structure. We swap their positions. And after we swap them, what do? You got it. We do our local checks again. Each of those two lines now has a new neighbor, so we check them to see if this swap created any new potential interceptions down the line. Okay, last event type. Our sweep line reaches the right endpoint of a segment. This line's journey is over, so we remove it from our status structure. But wait, we're not quite done. Think about it. The two lines that used to be its neighbors are now right next to each other. So we have to do one last check. Do these two, now that they're adjacent, intersect? This is crucial for catching intersections that might have been blocked by the segment we just removed. And this right here, this is the absolute magic of the sweep line algorithm. The reason it's so fast is that we only check for intersections between adjacent segments in the status structure. We are completely avoiding that O of n squared nightmare. We're keeping our checks local and targeted, and that makes all the difference. So let's recap the process. Every single thing we do is triggered by an event. A segment starts, two segments intersect, or a segment ends. And each of those actions is just a small local update to our status structure, immediately followed by a check of only the immediate neighbors. It's this disciplined, localized approach that gives the algorithm its power. This is all great in theory, but how do you spot this pattern in the wild? When you're under pressure in a coding interview. Let's talk about that. When you're faced with a problem involving geometry or intervals, here's the pattern you should look for. First, ask yourself, can I define a clear set of events and sort them along one axis? Second, can I define a status that tracks active elements along the other axis? If the answer to both is yes, you've probably got a sweep line problem. Just follow these 4 steps. Define your events, define your status, process the events in order, and perform local checks on neighbors. That's the core pattern. And this is why it's such a big deal. Following this pattern takes you from that slow, brute force O(n) squared solution all the way down to a super efficient O of n plus k log n. Here, n is the number of segments and k is the number of intersections. That log n part just comes from the time it takes to do operations on our status structure, like a balanced tree. This is the kind of massive optimization that interviewers love to see. And believe me, this is not a one-trick pony. This core pattern, defining events, defining a status, is incredibly versatile. You can use it to solve all sorts of problems. Need to find the total area of a bunch of overlapping rectangles? Sweep line. Need to find the closest pair of points in a huge data set? You can use a sweep line for that too. The fundamental idea is the same. You just change what your events and status mean. So now you have this powerful pattern in your toolkit. The next time you're staring down a complex geometric challenge or an interval problem, don't just jump to the brute force solution. Take a step back and ask yourself one simple question. Can I sweep a line through this?